Hello, AP Stat students. Today, we're going to continue our discussion of linear regression, and we're going to discuss residuals. We've mentioned this before. Recall that residuals are the distance between our actual data points on our scatter plot and the regression line, okay? Because not all of our points are going to fit perfectly on the regression line. So today we're going to dive a little deeper into that idea of a residual. If you look on the left side of the slide here, we have circumference in centimeters and weight in pounds of pumpkins. Okay, so that first entry in the table is a 72 centimeter circumference pumpkin, that weighed 11.24 pounds, etc. We'd like to investigate the relationship between the circumference and the weight of a pumpkin. Okay, so below we've sketched a scatter plot, actually we've made one, of the association of pumpkin circumference and weight of the pumpkin. And we use circumference as the explanatory variable. So circumference was here, and the weight was here. Okay, remember when you make a scatter plot, the first thing you want to do is discuss the association, which you've done here. We'd say there's a strong, positive, linear correlation between circumference and weight of a pumpkin. As the circumference increases, so does the weight. You can see that on the graph. You can draw a very loose line through there. And it looks positive, strong, and linear. Remember, we need form, direction, strength, and then the context statement. As the circumference increases, so does the weight of the pumpkin. Then the next thing we would do is find the least square regression line equation that predicts pumpkin weight from circumference. And we'd write it in context. So here's my calculator screen. Remember, A is the slope, B is the y-intercept. So my equation would be pumpkin weight, and remember we use the little caret, that means predicted, equals 0.44 times the circumference of the pumpkin minus 19.4. And 0.44, remember, is the slope, and that means that for every centimeter of circumference, the weight of the pumpkin increases by 0.44 pounds. So just a little shy of a half a pound per centimeter. And then the y-intercept is negative 19.4, which means a zero circumference pumpkin would weigh negative 19.4 pounds. And that is not reasonable, obviously. And the issue here is, if you look at the circumferences, none of the circumferences in the table are anywhere near zero, so we don't really know what's happening with the data. I think the lowest circumference we have in the data here looks like 48. So that's pretty far from zero, okay? And that's what'll happen if we don't have data that's around zero. Now, our least square regression line is our model for the relationship between our two variables. Unless the relationship between the two variables is perfect, there will be points that are not exactly on our regression line. And we already knew this. The distance from our data points to the regression line are called residuals. Okay? We find the value of a residual by taking our observed point and subtracting the predicted value from that point. Okay? The observed points, those are from the table, okay? And the predicted values are from the equation, okay? So to find a residual, you take the observed y and you subtract the predicted y, okay? You could think of observed as like the actual point, okay? The actual point on the graph, the actual numbers from the table, and the predicted value would be when I take that x value and plug it in, like the circumference, what do I get for the predicted weight? And the residual value is simply the observed y minus the predicted y. So you can think of a graph. Here's the regression line. Here's some points. The residual is this distance from the points to the predicted line. Okay? And we always find them by going observed minus predicted. That order is very important, and to help you remember it, it's in alphabetical order. Observed minus predicted. O comes right before P in the alphabet. So let's do an example. Let's calculate the residual value for a pumpkin that has a circumference of 60 centimeters. Okay, well, the observed value I can find very easily by jumping up to our table and reading the y value. So a 60 circumference pumpkin was 3.46 pounds. Okay, so that's talking about an actual pumpkin that was in our data. Like we had the pumpkin, we weighed it, this is the weight. Okay, So to find the predicted value, we would simply plug 60 into our equation and see what the equation tells us the pumpkin should weigh. So if I plug that 60 into the equation for x, for the circumference, and I solve that out, I end up with 7 pounds. So the equation tells me that that pumpkin that was 60 centimeters in circumference should weigh 7 pounds. But the actual pumpkin itself only weighed 3.46 pounds. So the residual of the 60 centimeter circumference pumpkin would be the observed y, or the actual pumpkin weight, minus the predicted weight. So 3.46 was the observation, 7 pounds was the prediction. The difference is negative 3.54. So what this means is that this pumpkin is one of these, where the actual pumpkin was lower than the prediction line. Okay? A negative residual tells you that the actual pumpkin was less than predicted. A positive residual would say that the actual pumpkin was more than the prediction line predicted. So interpretation of the residual at the bottom here, the 60 centimeter circumference pumpkin weighs 3.54 pounds less than predicted by the equation. Now, one of the things you have to be able to do is use the residual and the equation for a residual to answer different kinds of questions. So this says, if a pumpkin with a circumference of 50 centimeters had a residual of 5, what was the actual weight of the pumpkin? Okay, so, excuse me, this is what we have. We have a regression equation, which is the predicted weights of the pumpkins, right? And we know that a circumference of 50 centimeters had a residual of 5. Okay, which tells us that the actual pumpkin was 5 pounds more than predicted. Okay, now we'd like to know what was the actual weight of the pumpkin, or what was that observed value. Okay, well, what we could do is find the predicted weight and simply add 5 pounds to it. So how would we find the predicted weight of a 50 centimeter pumpkin? Well, we would plug it into our least square regression equation. So a 50 centimeter circumference pumpkin would be predicted to weigh 2.6 pounds. So that means this is 2.6. That's the y value for that point. Okay, and the actual pumpkin we know is 5 pounds more than that. So 5 pounds more than 2.6 would be 7.6. And we could get that by solving our equation. Residual equals observed y minus predicted y. The residual was 5. The predicted y from our equation was 2.6. When I solve this, I get an observed pumpkin of 7.6 pounds. So the actual weight of the pumpkin was 7.6 pounds. So I recommend drawing a quick picture like that. And I think it helps to illustrate what's happening. Remember, the least square regression line is the predicted line, and the residual tells you if your actual pumpkin was heavier, which would be a positive residual, or if it's lighter, that would be a negative residual. Here's another example. If a pumpkin with a circumference of 80 centimeters had a residual of negative 10, what was the actual weight? So again, we could draw a quick picture. Predicted line, circumference of 80, that doesn't really matter where you put that. Okay, so that'd be the predicted weight, but this pumpkin has a residual of negative 10, which means the actual pumpkin was 10 pounds less than predicted. So how could I find the actual weight? Well, again, I'm going to plug the 80 into our equation and get the predicted weight, which was 15.8 pounds. So that means this is 15.8. So the actual pumpkin would be 10 pounds less than that. If I subtract 10 pounds from 15.8, I get 5.8. So the actual weight of the pumpkin is 5.8 pounds. Again, I highly recommend drawing the picture and inserting the residual. I think that makes it much more clear what's happening. Remember, you can always find the predicted weight or the prediction of anything, of any x, by plugging it into the equation. Okay. Now, for some more information on residuals, if we add up all the residuals from every data point, they will cancel each other out, like standard deviation. Okay? So if you took all the positive residuals and all the negative residuals and added them together, they will add up to 0. So what we do then to work with residuals is we square all the residuals. Okay? Doing a linear regression makes the sum of these squares, these residual squares, be the smallest it can possibly be. That's why another name for the regression line is the least squares regression line. Now, the residuals as a whole can tell us a lot about the association between our two variables. We can make what's called a residual plot. And this is a graph of the explanatory variable x on the x-axis and the residual values on the y-axis. If you see a pattern or curve in the residuals, then the original data may not be linear. So we're basically going to make a new plot with our x values on the x-axis and the residual values on the y-axis. So we'd plot our pumpkin circumferences as the x values, but then instead of graphing the weight of the pumpkin, we would graph the residual for each pumpkin. Okay. So to do this, you'd go to stat plot, upper left-hand corner, and you'd see this screen right here. And what we want to do is change the y list to be the residuals instead of the pumpkin weights. So the calculator, when you do a linear regression, it stores the residuals in this variable called resid. Okay, but that does not happen until you've done the linear regression. Okay, so that has to happen first. So to replace that L2, you'd go to the list function, which is above the variables key. And the way to get that is to hit second variables. And under names, you'll see the screen right here, you'll see all the lists are there. And then any variables that your calculator has used over the years will be listed here. What we want to see is the resid variable. It may not be number 7 on your calculator. It might be further down. They're in alphabetical order, so you'd have to page down possibly to get resid. But you'd put your cursor blinking on the Y list, and then you'd hit the second variables, and then you'd page down to residuals, and you would click on the residuals. That'll insert it into the Y list. So your screen would look like this, on the bottom here. So resid takes the place of the Y, or excuse me, of the L2, and then you would do the zoom 9. And you get this residual plot. Okay. Now, with a residual plot, you can think of this as here's our regression line, here's our scatter plot around it. Okay. What a residual plot is it takes the regression line, okay, and it basically makes it be the x-axis. So then like this residual that's above the x-axis would end up being over here on this graph. Okay, and any of these points below the x-axis, those would end up being below, or I'm sorry, these points that are below the regression line would end up being below the x-axis. So the graph up here, the residual plot, all of these points were above the regression line. They have positive residuals. And all of these points were below the regression line. Those have negative residuals. Okay. Now, what this graph gives us is a clearer picture of the association between the two variables. Okay. There are things in the scatter plot that we will not be able to see because of the scale and the magnitude of it. But when we look at the residual plot, new details emerge, and we'll be able to see patterns that we could not see in the scatter plot. Okay. So how do we use this? Well, if the residual plot looks random and the residuals are scattered about both sides of the x-axis and they have a uniform spread about the x-axis, that is evidence the association between the variables is linear. So what a residual plot is a test for linearity. Okay, it tells us, it gives us more evidence that our association between our two variables is linear. Okay, so we always want to check a residual plot as part of our linear regression to see and make sure that the original data was linear. So looking down here at the pictures, these are examples of residual plots. This residual plot right here is evidence that the original graph was linear. Notice the points are randomly scattered about the regression, or about the x-axis. This is the x-axis right here. I don't see any pattern. They have a pretty equal spread around the line. Like there's nothing that looks like an outlier. So that residual plot would tell you that your data was probably linear. If you look at the second graph, which I'm going to circle in blue, this residual plot shows a definite pattern. Okay, you can see that the dots actually make what looks like a parabola. Now, what is happening with this one? I'll draw an example over here. Is that here's the regression line in black, and here are the points. So what this is showing you is that the data points, the red dots, were not linear to start with. Okay, and the thing is, when you make a scatter plot, sometimes you can't see that clearly in the scatter plot. But when you go to the residual plot, it becomes super obvious. So in this case, we would say the original data was not linear. And the third one, I think you can see, is just the opposite. The points go like this. They're not, you definitely see a pattern. This is kind of what can happen here, is that these points can look really close to that line, where you might not be able to see it in the scatter plot. But if you look at the residual plot, you can see it for sure. Like you see these two dots that are below, in the residual plot, they're here. These points that are above the residual or the regression line look like these points right here. And then these points that are below again would represent these over here. So you can see it's harder to see the pattern in the scatter plot, but it's easier to see it in the residual plot. And that's the value of the residual plot. So here's a couple more examples. On these, I have to draw in the x-axis. So remember, the x-axis is basically takes the place of the regression line. Okay, so you can see the first graph. I'll label it number 1. This one looks linear because if you look at the residuals, they're all random and scattered. I don't see a pattern anywhere. So we'd say that that residual plot supports that the graph was linear. For graph 2 on the right, if you look carefully, I think you can see the pattern. When there's a pattern like that, that means that the original graph was probably not linear. And the third one on the bottom left, number 3. This one, if you look, the residuals start off pretty close to the line, and then they jump pretty far away. And they did that on the bottom too. Okay. What this is an example of is, right here, the residuals are close to the line, which means you could probably make a pretty good prediction using the regression equation. On the other side of it, though, where the residuals get pretty far away from the line, probably not a good prediction would be made from that situation. Okay? So the residuals can kind of tell us how good our prediction might be. Okay? That example number 3, we probably don't want to use that line to make predictions in the green area. Keep in mind that is the goal of linear regression, is that we want to be able to make some predictions. For the fourth one, if you count the residuals on the positive residuals, there are 5. And if you count the negative residuals, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so there's not an equal distribution of data points above and below the regression line. It's because of this one over here, which we would probably call an outlier. Okay, that one residual is balancing out multiple residuals on the bottom, because remember, residuals cancel each other out. So this time the least square regression equation would not be good at predicting. Okay, trying to write on this. So we want to see random scattered points around the x-axis. We do not want to see a pattern like in number 2. We do not want to see the spread of the residuals getting increasing as you go. This example number 3 actually has a name in statistics. It's called the plot thickening, which means the spread is getting thicker and thicker as we go. Okay, we don't want to see that. And we want an equal or pretty close to equal distribution of residuals around that x-axis. So in that 4th case, there wasn't an equal distribution, so the least square regression line would not be good at predicting. Good luck with your residual homework, and if you have any questions, contact your teacher.